Hey folks, time for another tutorial. Today we're going to go back to the synthesis world and look at a new instrument called MULTIWAVE. So I'm going to load MULTIWAVE. And MULTIWAVE, as you might have guessed, is similar to wavetable, but it's a wavetable on steroids, so to speak, because it allows us to synthesize multiple waves using a single instance of itself. So to do that, we are going to create the following variables. We can say envelope, make table, line, not loon, line, 3000, 0, 1, 1, 2, 1, and 3, 0. So pretty classic envelope. Then st0, doer equals 2, the usual suspects, amplitude 8000, and WF for waveform, and we use make table again, but with the wave table type, same table size and sign, and we're going to pass all these variables to MULTIWAVE. So here we go. So it's to say start door amp times env and then WF, and here's the interesting stuff. So I'm going to type this in the next line, but keeping the parentheses, of course, and I'm going to type 100, 1, 0, and 0.5. So what do we have here that is substantially different from wavetable? So one minor thing is the order of the arguments. So we have the position of the waveform argument appearing after the amplitude, which in wavetable is usually followed by the frequency. But we also have this sequence of 4 values at the end, and what these values stand for is the first one is the frequency, so we have 100 hertz. And the second one is something called the amplitude multiplier. And by amplitude multiplier, it means that whatever number you put in here is going to be multiplied by whatever value you have as amplitude, and that's going to be the real amplitude of MULTIWAVE. And I'll explain why you have to do this multiplication. But then we have this next argument, which is the phase, and it's something that we're not going to deal with right now because it's not very relevant, but just in case you're curious, phase is a value between 0 and 360, which is, as you might guess, expressed in degrees. And then we have the panning, so we have 0.5 for the middle, and if we play the script, yeah, super impressive. But what if I were to add another, what if I were to add another series of 4 values? So I can say 150, 10, and 0.5, and if I play it, okay, what if I add another one? So 200, 1, 0, and 0.5. Oh, yeah, so you can keep adding and adding groups of 4 values and have multiple waves sounding at the same time, but we're not interested in just adding waves to create chords, and that's definitely not what MULTIWAVE was made for, I think. Instead, we can use MULTIWAVE to do something called additive synthesis. And additive synthesis is a very old technique that allows us to create timbres by virtue of adding an indefinite amount of simple waveforms, in most cases sinusoidal waveforms. So here's what we're going to do. So we're going to type the following. So the first thing, we need to create a variable called fund for fundamental frequency, so 100 hertz, and then I'm going to create a variable called brightness equals, let's say, 1.5, and I'll explain what this is in a second. Then we're going to create partials, so the number of waves that we're going to have inside MULTIWAVE. And then I'm going to create a list, an empty list that will be called spectrum. And then we're going to use a loop to populate this list. So we can say for I equals 0, I I less than num partials times 4, and then I plus equals 4. So every time the loop runs, this I variable, which will be the index for the elements that I'm going to insert inside the spectrum list, will increase by 4. So here we go. So we can say that spectrum, the ith element, I know that sounds weird, but the ith element of spectrum will be the fundamental frequency times I plus 1, so that it doesn't start with 0, because if the first one will be 0 and we don't want to have a frequency of 0 hertz. And so this one would be the frequency. Then we have spectrum. The ith plus 1 element of spectrum will be a random number between -1 and 1 divided by the variable brightness to the power of I. So this is going to guarantee that the higher, or the higher the frequency, the lower the amplitude. So we have the amplitude, then we have spectrum. So the ith spectrum, the ith plus 2 is, element of spectrum will be 0 because it's phasing, and we don't care about the phase right now. And lastly, we have the ith plus 3 element of spectrum will be a random number between 0 and 1 for panning. I forgot to say here that this is the phase of the wave, and we can get rid of all these values and pass the list spectrum, which by the time we get to MULTIWAVE, it will be populated because of this loop. So we can play this. So it's very soft. So I'm going to add a variable in here called master to make sure we can just make it louder if we want to. Let's say 3. Yeah, so we can hear. And we are more or less perceiving this as a unified timbre rather than a chord. But we're dealing exclusively with a harmonic distribution of frequency so far. But something we can do is turn this harmonic spectrum into an inharmonic one, meaning something that doesn't preserve this harmonic relationship between the frequency. So one way of doing this is by adding a variable called Distortion, which allows us to compress or expand the spectrum. And so we can type here, we can type dist for distortion, let's say 0.85. And inside the loop, we're going to say that partial, new variable partial, will be equals to fund times I plus 1. So the same thing that we have here, and we're going to get rid of this, and we're going to say that distortion times, and open parentheses again, partial minus fund plus plus fund. So this is going to distort the interval in between each of the partials. And if we play this, we get a less predictable type of timbre. And so what can we do with this? So we can start by applying a more realistic envelope using the curve table type, which we haven't looked at. And it's similar to line, so I'm going to change this to curve. So it's similar to the line table type, except we can control the curvature of the lines between each point by adding an extra value in between each of these pairs. So we can say that 0, 0, 2, then 1, 1, 1, minus 2, and I'm going to say that this one is going to be 0.25 and then minus 2, and then I'm going to make this a little sharper in 2000. And if what I just did doesn't it doesn't make any sense to you, hopefully these two pictures that I have here will help you understand better. So let me open these two. So the first one shows you how if you have a positive curvature value, the hump of the curve will be closer to the initial value, and faster approach the next one towards the end. And so that's what happens when you have a positive curvature value. If you have a negative curvature value, the hump will be closer to the new value. So you can see that that's what's happening here. And the second image shows us that the more you deviate from 0, the steeper or the more pronounced the curve will be. So assuming that this is clear enough, we can go back and play this. So we get sort of a, let me make this louder, let's say 7. Yeah. So we can start playing with this, and we are going to go to the next thing on this tutorial, which is applying tremolo, amplitude tremolo, with a function that is similar to make table in nature, called make LFO. So make LFO, and make LFO. So let me create this variable called tremolo, trem. And make LFO takes 4 arguments. So the first one is the wave type. So I'm going to type sine. Then the next one is the frequency. So let's say 5 Hertz. And the next 2 arguments are the minimum amplitude. So I'm going to say 0.5 and 1. And all we have to do to get the tremolo is multiply this variable with the make LFO function with the amplitude. So I can say amplitude times trem, and if I play this, excellent. So of course we can't finish this tutorial without putting all this stuff inside a loop and randomizing a few things. So let's do that. So everything will be inside a loop except for the envelope and the master variable, and I'm going to get rid of start because that's going to be our counter variable for the loop. So st equals 0, st less than, let's say, 10 seconds, and st plus equals, and I'm going to randomize the rate, so 0.01 and 0.2, and I open curly braces, I close the loop with curly braces, and I'm going to create, let's see, where do we have this? I'm going to create a variable called pitch, like we did in another tutorial. So pitch big rand, I'm going to say, let's say 60, 65, and 67. And another variable called octave, big rand, minus 24, minus 12, 0, and 12. And we are going to use the CPS MIDI function, pitch plus octave, Jesus Christ, octave, and we are going to randomize, let's say, the duration, so something like 3 and 6.5. We're going to randomize the amplitude, so let's say 15,000. Let me take it down a little. What else can we randomize? We can randomize the brightness. So something I didn't explain about brightness is the brightness is the closer it is to 1, the more even the amplitudes of each partial will be distributed. So if you have 1, basically all the amplitudes will have the same, will be at the same volume, and if you have 2, they will be sort of like curved. So the higher the amplitude, the softer they will be. So we can randomize this by, let's say, 1 and 1.2, and I can also randomize the distortion. So let's say irand, so 0.1 and 2. what else can we randomize? I think that's all we can we can of course randomize the frequency of the tremolo. So let's say 3 between 3 and 6. Oh, I forgot to say IRAND 3 and 6. We can randomize this by saying 0.3 to, let's say, 0.8. And I think it's time. So let's hear this. Beautiful. So there you have it, an immersive experience with bell-like sounds by using MULTIWAVE to do additive synthesis in RTcmix. So as per usual, try things out on your own before moving on to the next tutorial, and leave questions or comments if you have any, and thank you so much for watching.